All right, so good afternoon and welcome everyone to the fundamental theorem of Starithmetic. Our presenter today is Travis Kowalski from South Dakota School of Mines and Technology. If you have any questions for the presenter during the session, please feel free to enter those into the chat at the bottom of the Zoom room screen, and we will address them at the end of the talk. So on that note, I'll go ahead and hand it over to you, Travis.
Thank you. Still says the host is disabled sharing.
Oh no, one moment. Oh, there we go. It should work for you now.
That looks good. So let's go to here. And can everyone tell me if they see a screen?
Yes, we can.
Excellent. So I'll put that over there. So I'm Travis Kowalski from South Dakota Mines, and I'm going to be talking about the fundamental theorem of Starithmetic. And that's really kind of a misnomer. That's more of a clickbait title. There isn't a grand theory of Starithmetic yet. And I don't know if the result I'm about to share with you is the most important part of it, but it sounded a lot better than the official, real, authentic title, The Uniqueness of Factorizations of Star Contours into Laterally Independent Irreducible Substars, which would be the more authentic title. So let's get into it. So we're going to start off we're going to do some 5 quick parts. The first part is talking about star polygons. So we're going to let 0 denote the unit circle and 0 into n denote the set of n evenly spaced points around the circle starting at the point 1, 0. So in complex terms, these are just the nth roots of unity. And we're going to call a standard star the set of those points formed by connecting each nth root of unity to the point 2 slots away from it. So there's the formal definition right there, but it might just help to see pictures. Here are the examples of the 1, 5 star, the 2, 5 star, the 3, 8 star, and the 2, 8 star. So the 2 stars on the left have 5 points. And in the first example, each point is connected to the point 1 away from it. In the 2, 5 star, each point is connected to the vertex 2 points away from it. So that's just how that symbol works. More generally, a star polygon is any shape you can get from one of these standard stars by rotating, dilating, and translating to some other point in the plane. And we're just going to consider all of them to be equivalent. So any regular pentagram is the 2, 5 star. Any regular pair of interlocking squares is the 2, 8 star. Some basic facts about this notation. Any single star can be represented infinitely many ways. So it can be represented as the fraction k over n. It's also negative k over n, because whether you connect up or connect down, you'll connect back anyway. And if you add any multiple of n, you just go around the circle and still connect at the same point. There are 2 stars that are exceptional that are at least worth mentioning. The 0n star consists of n points with each point connected to itself. So that's just going to be the nth roots of unity. It's a disconnected star. We're still going to call it a star of n sides. We're just going to think of each of those sides as being of length 0. And if n is ever even, the star n over 2n is an asterisk. It is an n-pointed asterisk where each point is connected to its antipode across the circle. We're still going to call that an n-sided star because you go from antipode here and then from the antipode back again. It just happens to be that those 2 sides lie on top of each other. Now, I'm going to have to point out that there is already a symbol that exists for star polygons, the Shapley symbol, which came into being in around the 1850s and has been used for nearly the past 200 plus years. It takes the same star, but it uses the reciprocal. So what I'm calling the 2, 5 star, Shapley would write as the 5, 2 star. And he has the further restriction that k is always positive and smaller than n over 2, so as to prevent that multiplicity of naming conventions. So since this has been around for quite a long time and it's used in the theory of polytopes, I should maybe give some reason for why I'm rejecting it out of hand. So to do that, let me give you some geometric descriptions. I'll tell you a couple things about the star k over n. Every vertex angle on a star like this measures pi minus 2 pi k over n radians. The angle between 2 vertices measures the same thing plus an extra pi over n. The 2 bounding circles, the interior circumradius or the circumradius and the inscircumradius, have a ratio that is exactly cosine of pi times k over n. And any side of one of these sweeps out an arc that measures 2 pi k over n radians. I don't expect you to memorize any of these numbers. I just want to point out that every geometric property of these stars involves the fraction k over n, not n over k. Additionally, if you use the skip over sides, then every single polygon can be written as 1 over 3, 1 over 4, 1 over 5 reciprocals. And so you can write this terrible pun. But there are better reasons for why we're going to go and do this switch right here. And so let me start to give you some reasons for them. So the first thing I want to do is talk about a concept that people who play around with star polygons know, but I don't think it has a name yet. So we're going to call it lateral dependence. So the basic idea is pick any star you'd like. So I've got the 2, 8 star right there. Inside the 2, 8 star, if you look at a subset of its sides, there's a 1, 4 star hidden inside of it. On the other hand, if you were to take all 8 sides of the star and shrink them down by about 67%, you would end up with a 1, 8 star. On the other hand, if you were to take that 2, 8 star and extend each one of its sides, you would end up with a 3, 8 star. So this idea that some stars are stretched multiples of other stars reminded me an awful lot of the idea of linear independence. And so we're going to call this lateral dependence, with lateral meaning side. So a star polygon is laterally dependent on another one if some subset of sides of T can be either shortened or lengthened sufficiently to form a star that's equivalent to the first one. And we're going to use, say, S is laterally independent if it's not laterally dependent. So we've seen that the 1, 4, 3, 8, and 1, 8 stars are all laterally dependent on 2, 8. Conversely, the 2, 8 star is laterally dependent on the 1, 8 and the 3, 8 stars because you can just shrink or stretch those lengths. But the 2, 8 star is laterally independent of the 1, 4 star because the 1, 4 star is a 4-sided star. It doesn't have enough sides to span an 8-sided star. So one question to ask is, how do you tell if one star is laterally dependent on another? There's a way to answer this question pretty easily. And we'll do this by a thought experiment. Imagine taking the set ON, the nth roots of unity, and through each one of those roots, draw a line tangent to the unit circle. So the tangent through the point 1, the tangent through the point 2 pi j over n, the tangent through the point 2 pi j over 2n, on down the line. This object is definitely not a star. It's infinite in length. But if you think about any n-sided star and just stretched each one of its sides infinitely long, indefinitely, this is the shape you would get. Every single star, n-sided star, if its sides are extended indefinitely, will form this object, which I'm denoting z over n. Said differently, this piece of geometry contains every possible star that's laterally dependent on an n-sided star. And so in this piece of geometry, every n-sided star exists. In fact, you'd find it by just intersecting this shape with a circle of radius secant pi k over n. And here are 2 examples. Here's the z over 8, and I've drawn the circle of radius secant pi 3 over 8, secant pi 2 over 8. So you can see the stars embedded inside of each other. This argument shows that any 2 n-sided stars are laterally dependent, because if you extend out the sides of any 2 n-sided stars, you end up with that set z over n. More generally, an n-sided star is going to be laterally dependent on a q-sided star if and only if n is a divisor of q. The basic argument just being, if you've got one small star dependent on a larger star, that means that the small star lives inside that big set z over q. If you extend the lines on the small star, then the z over n of the small star will be a subset of the z over q of the large star. And that means they have to at least be a subset of the points on the unit circle, which is only true if n divides k evenly. So now we're going to start talking about star contours, and this is where we're going to get to some new results. So the standard stars are these static objects. They're just sets in the plane. So what I want to do is give each one of their sides an orientation, turn them into vectors if you'd like. That will orient the stars globally. So if I have a line segment, I can think of the segment that goes from the point zeta to the point psi, and here's a parameterization for it. And so if we took the union of each of those parameterizations from one point on the endpoints of unity to the spot 2 away from it, the union of that contour, which I've written down in function form down there, is going to be k over n by definition. But this object is not a static star. This object is a collection of functions. It's a contour in the complex plane. And so we're going to call it a star contour. So star contour is essentially a standard star where we have directed each one of the line segments. In the case, since we can change the numerator, K over n and m over n define the same star contour if and only if they differ by a multiple of n. And negative k over n is the opposite of the contour k over n. Same shape, but reversed orientation. And we can kind of see this in a picture. I will show you the oriented 2-5 star. So it starts off by taking the line segment that goes from 1 to e to the 2 pi j times 2/5. Yes, I'm one of those guys who use j instead of I. Come at me. Then we take that line and we rotate it by 2 pi times 1/5 radians, or 72 degrees, to get this line segment. Rotate it again, and rotate it again. The upshot is that we've still drawn the 2-5 star, but now it has this global counterclockwise or positive rotation. On the flip side, the negative 2-5 star is the exact same image, but now all of the arrows have been oriented in the other direction. It gives it this global clockwise orientation. The notion of this orientation too can be made precise because these are functions. We just take the winding number of these contours. So if the winding number is positive, we're going to say that the star is positively oriented. If the winding number is negative, we're going to say that the star is negatively oriented. We can use the winding number as a numerator if we want to talk about a standard form. The two exceptional stars, the 0 star and the n over 2 over n stars, we're going to assign no orientation to those. In the case of the 0 over n star, it's disconnected. None of the points circle the origin. And in the n over 2 over n star, it passes right through the origin. And so this winding number formula explodes. So we're just going to assign no orientations to those two. So in terms of drawing pictures, I want to be able to distinguish these things relatively quickly. And so I'm going to use color. So whenever I draw a black star, it's just going to be the static image of a set. When I draw the same star in blue, I'm meaning the star that has a positive rotation. When I draw the star in red, I'm meaning the star that has a negative rotation, so turning clockwise. So in this case, I have drawn you the unoriented 2-9 star, the oriented 2-9 star, and the reverse oriented 2-9 star. So let's talk about the arithmetic part, the star arithmetic part. The notion of lateral dependence describes how you could take a big star and find smaller, that is fewer sided stars inside of them. So I want to go in reverse. I want to take two small stars and combine them together to form a bigger star. So if the two stars are k over n and p over q, I'm going to motivate how I'm going to define this operation. So first, the number of sides of the big star. I'm going to set it to be the least common multiple of the two stars I build. That way, the star that they compose will they'll be laterally dependent on it. So I can reconstruct each of the two smaller stars from the thing I build from them. As for the skip step, how I'm going to jump from point to point to point. Well, each one of the individual stars describes an individual arc. So the first star says sweep out k over n of a revolution. The second star says sweep out p over q of a revolution. And so for my combined star, I will sweep out one followed by the other, and then multiply that by the total number of points I've got. That's the skip. That's how far I'm going to go. So there's the formula down there. A times k over n plus p over q. That's how much of a rotation I'm committed to. And b is the number of points I've got in the star. And so I can write the formula out here if you want to see it as an actual and honest to goodness fraction. The one thing that's worth pointing out about this fraction is that it's ill-defined. There's more than one symbol for one of my stars. If I have the 2-3 star, that's the same as the 5-3 star. That's the same as the 8-3 star. And so k and p can change in this formula, which means a is ill-defined. However, if I replace k by any other number whose equivalent to k mod n, and I replace p by any number whose equivalent to p mod q, and plug those into the formula, the result is something who differs from the original value by a multiple of the least common multiple of n and q. It's a long way of saying that while a is ill-defined, the star a over b is not. It's well-defined. And so we're going to use that as a definition. I've got two oriented stars. I will combine them by building a star whose number of sides is the least common multiple of the sides of the two, and whose skip step will be the sum of those two objects treated as rational numbers and then multiplied by the total number of sides on the shape. As a side issue, you can also motivate this completely algebraically without having any recourse to geometry by doing the pairwise multiplications of the rotators and the endpoints on each one of the line segments, and it will end up with the same result. But maybe what I should just show you is what it looks like. So if you took a 2-7 star and a 1-6 star, when you add them up, or combine them, sorry, you're going to get a 42-sided star. The skip step will be 42 times the sum of these two fractions, which is 19. Or in pictures, if you take a positively oriented heptagon times a positively oriented hexagon, you get the positively oriented Ruth Bader Ginsburg descent color. On the other hand, if you take 2 7s and combine it with 5 6, the end result is a 4742, which is equivalent to a 542 star. In other words, the positively oriented heptagon combined with the negatively oriented hexagon is this bracelet-looking thing. And the point of this example is it shows you why orientation matters. If I didn't ascribe an orientation to it, there'd be two possible outcomes. Two more examples, the 3/8 star and the 512 star will combine to get me the negative 524 star, which is illustrated below. And the 3/8 star and the negative 512 star, when combined, yield the negative 124 star, also shown below. The point of these two examples right here is to show you that the orientation of the combination is not easily computable from the orientations of the two stars we put together. Last but not least, I've got two more examples. If I take the 1/3 star and add it to the 1/6 star, that's a 6-sided star who has a skip step of 3. So triangle combined with hexagon equals asterisk, if you'd like. The 2/6 star combined with the 1/6 star is also a 6-sided star that has a skip step of 3. So the Star of David combined with the hexagon is equal to the same asterisk. And this last part right here is what's going to jump us into our next section, talking about the arithmetic rules that we get from this definition. Some of the arithmetic properties are pretty basic. This operation is commutative, it is associative. It's very easy to see that the one-sided star, the 0.10, the 0, 1 star, is an identity. And that if you negate a combination, that's the same thing as the combination of the two individual negations. But because combination always increases the number of sides, no star other than the identity has an inverse. So this is not a group. And we saw an example that showed that ST equaling RT didn't necessarily imply that S and R were the same. So it's not even a semi-group. So I've lost some cool algebra properties that I might hope for. So the only thing that I'm going to end with is, could I say anything about the factoring of these stars? Like, say we want to take 1115 and factor it into two pieces. If I were to factor it into two stars, okay, 4/45 and 7/45, that's an easy factoring, but that's stupid. Usually we would like to have fewer sides. We'd like to factor in smaller pieces. One option would be to have a 5-sided and 9-sided star because their least common multiple has to be 45. So how do you find integers so that if I take the A/5, B/9 star and combine them, I get the 1145 star? That means solving the equation 9A plus 5B equals 11. One solution is 4, 5. Another solution is -1, 4. And both of these describe the same stars. On the flip side, if I were to go and say try a 15-sided star and a 9-sided star, I would go and discover that there are multiple solutions who correspond to different stars. So when can a star be factored into smaller stars, and when is this factorization unique? So let's give a quick definition. We're going to call a star reducible if it can be factored into two stars that have a smaller number of sides, and irreducible if it's not. Any star with a prime or prime-powered number of sides is clearly irreducible because the least common multiple of two powers of primes is going to be whichever one had the larger power. But it turns out that this sufficient condition is also necessary. We have something called the Factorlemma that says that an m-sided star with m and n being coprimed can factor uniquely into an m-sided star and an n-sided star. The basic argument is what we were looking at previously. If I have the equation xn plus ym equals k, there is an integer solution provided n and m divide k, and if m and m are coprime, this is always true. And if I take that solution, a/m and b/n is one star solution. And if I were to take any other possible solution and go through the act of solving like we were doing before, the Diophantine equation that we solve ends up coming with solutions who differ from the original solution by multiples of m and n, which means that the resulting stars are the same star. So if we were to try to factor the star 73, 120, we could break that up into the number of sides into 3 times 40. Those are coprime. And so if we solve the equation a times 40 plus b times 3 equals 73, by inspection, I can pull this solution out, and that's the only solution in stars. 40 is still factorable. So if we factor 40 into 5 times 8 and solve the corresponding solution, we can break up the 1140 star into a 2 8-star and a -1, sorry, a 2 5-star and a -1 8-star, which means that we factored 73 1/20 into irreducible stars. If this factorization is unique, we'd have something called a fundamental theorem. And unfortunately, it is really not unique. There are lots, unless there are infinitely many ways, in fact, to factor star into irreducible stars. But in this list that I've shown here in symbols, you notice that they get longer and longer and longer. The shortest one in this list, every single one of the stars in that short list is laterally independent from each other. And it turns out that that's a theorem. Every star contour can be represented as a unique up-to-order combination of irreducible, laterally independent stars. And this factorization is the shortest of all of the possible factorizations into irreducible stars. Now, we're kind of running short on time, so I'm going to jump by the proof of this just to end with 2 observations. Even though this collection is not a group, it has a really nice relationship to cyclic groups. The set of all stars, n-sided stars, is actually isomorphic to the cyclic group Z mod n. And so this set is built out of these sort of nested collections of cyclic stars. And the stars themselves are nice visual representations of the cyclic subgroups generated by the individual elements of the group. So for example, the 1 12-star and the 5 12-star are illustrated here, and they show the path of a single point as it's being added to itself iteratively. Whereas if you have an element who's not coprime with the order of the group, then we know it's going to generate a proper subgroup that has cosets. And so for example, 3 in Z12, the group generated by 3 is 3, 6, 9, and 0. The other 2 cosets are actually the other parts of the 3 12 star. So there's this really nice geometric interpretation of cosets as just laterally independent subcollections of a big star. I'm going to skip this by row here. The one thing that I haven't talked about here is other directions that people might go with this. So there's an operation called duplication, which causes a repetition of stars. And there's a geometric idea of inverting a star through the unit circle. And there's evidence that suggests that these 2 objects might be related by a form of duality, which means if we were to add these cyclic stars in with our current stars, we might be able to build a bigger group from this term. And I'm going to close with a shout out to one of my advisees, Sarah Riley. She actually built equivalence classes instead by saying that stars are equivalent if they can be built by duplicating a fixed star. And she showed that under this equivalence class, negation and combination are well defined, that the set of simple stars is a group isomorphic to Q mod 1, that the simple stars can be factored into polygons infinitely many ways, but that the factor theorem still remains, that they can be factored into irreducible stars that are laterally independent and one way only. And so with that, I will call it quits.
Perfect. Thank you so much, Travis. And it looks like, yep, we are right out of time. So we appreciate you sharing all that valuable information with us today. If you do have any remaining questions for the people attending, feel free to stop by the Hawks virtual booth to speak with a member of our team. Then the next session will begin in just a few minutes. So you can view the chat for the session meeting room links or access the conference website for a complete list of sessions and their descriptions. And again, don't forget to swing by the Hawks virtual booth for the opportunity to win that $50 Amazon gift card. And we are going to be seeing everyone in the next session.